Hi everyone, my name is Bhaskar Gyan, as you might already know, and I work at Angel One as Senior Staff Engineer. And today I'm here to talk about how you can supercharge your server-rendered pages so that your end user need not to wait. Picture this. You have spent days, even weeks, creating a perfect web application. It has sleek design, cutting-edge animations. You have even optimized your APIs so that everything on the backend is running lightning fast. Everything looks perfect. Now your user gets the link, they click on the link, and 1, 2, 3. 3 seconds is gone. User is still staring at the empty white screen, and they decide to move on. Do you know 53% of your user will abandon your site if the page takes more than 3 seconds to load on a mobile device? All the hard work, all the beautiful design, everything was lost just in the matter of few seconds. There are other studies done to correlate how improvement or how the user experience relates to the business impact or business growth. As per one of those studies, 88% of your online consumer are less likely to return to your site after having a bad experience, and page load is one of those bad experience. There is another study which measures the impact of the improvement in page load and how it impacts the conversion of a page. So as per this study, for improvement of just 100 millisecond or 0.1 second in the page load in a mobile device, for a retail site, they saw a jump of 8.4%. For a travel site, that jump was close to 10.1%. This means we cannot ignore the performance when it comes to web app. I will go into detail of this. Before that, let me take you through the UI architecture, what we are following at Angel One. So in Angel One, we have selected SvelteKit and Tailwind as our primary tech stack. Now, in the interest of time, I won't be going into detail why we have selected this, but performance was one of the reason. Now, for a user, they can choose to open our page either inside our Angel One Android native apps, Angel One iOS native apps, or they can choose to open it via normal browser. It can be a mobile browser or a desktop browser. In case of our native apps, we are opening our pages inside a web view. Due to this, performance was even more critical for us because we don't wanted our user to feel a disconnect when they're navigating between different parts of the app. Now, once the request originates from any of these mediums, it will go to Cloudflare. From Cloudflare, depending upon the path what the user is trying to access, it will forward to the appropriate load balancer. Then again, load balancer, depending upon the load, it will forward those requests to our ECS container. ECS container is where our SvelteKit app resides and which is wrapped inside a Node.js server. Also, our ECS container and our backend both are inside the same VPC. I will come to detail of this, how we are leveraging this setup later during the talk. Now, once the load balancer forward the request to our SvelteKit, SvelteKit then gets the data either from the cache or it calls a backend API, gets the data, create the HTML, and we send it back to the client. So what can go wrong here? While optimizing for server-rendered pages, the main challenge comes in finding these bottlenecks of performances. It can occur anywhere, the time when the server is trying to process the request or the time when the browser is actually trying to render the content. It can have a severe impact on the page load and overall user experience. On the server side, the inefficient code or data processing can be one of the bottlenecks. For example, if your server render page depends upon huge amount of fetched and processed data, it can slow the rendering process down. In the same way, inefficient caching strategies can also be one of the bottlenecks. What it means, if you are not caching your server generated content well enough, or you are not caching the APIs which are responsible for generating those content, then it will put an unnecessary strain on the server, resulting in slower response time. Then network latency. This is also one of the critical bottleneck. This impacts mainly if your user is trying to access your content, maybe on a slower network, or they are trying to access from a remote. In absence of CDN or edge servers, your page load would be considerably slower for those users. Till this point, The server is then processing the request, it generated that HTML, then it sent it back to the browser. Once the browser gets that HTML, it first need to pass that HTML to know what all content or what all assets you need in order to make this page interactive. So during the front-end rendering, again the bottleneck can come in the shape of maybe due to huge JavaScripts or unoptimized DOM manipulations, which can cause frequent reflow repaints. Then another thing would be another unoptimized assets. So another unoptimized assets like CSS, fonts, images, those can also create the bottleneck. CSS by default is a render blocking resource. What it means, until and unless your CSS file is not loaded, browser is not going to show any content to the user. This is mainly to avoid flash of uninstalled content. In the similar line, fonts. Fonts are also kind of render blocking resource. What it means, until and unless your custom fonts are not loaded, browser is not going to show any text. The text, the font on which the font depends. So it will hide that text. The moment your font is loaded, it will apply that font, then it will show that text. This is known as flash of invisible text issue. Again, not a good user experience. So how will you know how your web page is performing? Is there any metric for that? The answer to that is yes. So there are web vitals from Google. Now, web vitals are kind of a health check for your app. Web vitals divided into two parts. One is core web vital, which includes LCP, INP, CLS. LCP mainly deals with the loading performance of the app. INP is the interaction to next page, which deals with the interactivity, and CLS tells how visually stable your page is once your page is rendered. INP, CLS, those are post-load metrics. In the similar line, there are other web vitals like TTFB, FCP. TTFB is the time to first byte. It includes the time when your server is busy processing the requests, is the time when your user is actually seeing that empty white screen. Plus, that includes any of the DNS, SSL time, or if there is any redirect, if you are doing. It includes all those times. Then FCP is the first contentful paint. This is the time when your user clicks on the link and they are seeing something meaningful on the browser. So that users are assured that something is happening. I clicked on a link and something is happening. Now, there are certain thresholds defined for all these metrics by Google. For example, in the case of FCP, you should try to load your or show some meaningful content to your user within that 1.8 second. For it's a P75 metric. So percentage 75 users should see your content within 1.8 second. Similarly, for LCP, that threshold is 2.5 second. Now, the more your TTFB time or the more time server is trying to process the request, it will push your FCP. The more the FCP is pushed, it will push your LCP even further. So, if you are trying to say optimize for LCP, a good starting point would be to look into your TTFB first, then look into your FCP, then go to LCP specific strategies. Then these are the health check number which we need to find for our page. But now the question is, how will you know your numbers? For that, there are different tools available online. Some of them are from Google, some of them are from other third party. Starting with Lighthouse. This is the most famous tool. If you are active on Twitter, you might have seen a lot of people posting their Lighthouse score of 90, 95, 100. In the similar line, there is another page speed insight. This is again from Google. Only thing is like this is a controlled environment from Google and which uses Lighthouse under the hood. And it's an online portal. Then there is a Yellow Lab tool. Then there is a pagespeed.compare. It's a quite nice site if you want to compare against your competitor, your site. You can put all those links. It will give a full detail of your page against your competitor. Then there is a web page test. So web page test is quite nice in the sense it gives you detail right from the time your test environment initiates the request to your server till the time your page is fully loaded and is interactive, and whatever is happening in between those. Plus, it gives a good suggestions on things which you can improve on your page. But there is a problem here. All these are lab-based tools. That means the test is running in a controlled environment, which might not reflect how your actual user might be using or perceiving your page. So what's the solution for that? For that, there is a real user monitoring, RUM data. Now, RUM data is something which Google's collect on your behalf anonymously, considering your page is not behind an authentication, considering your page is crawlable, then the user who is trying to access your page inside the Chrome needs to be logged in to the Chrome. And plus there are a few default settings also. On top of this, Google don't collect the data if you're opening the page from a web view. So that was kind of a deal breaker for us. So what's the solution for that? How will, if you want to track your pages from a web view, or if you want to track the performance of the behind authentication pages, for that there is a Web Vital plugin. It's a very lightweight plugin which you can add to your page, and it will start getting all those Web Vital data for you. From there you can pipe those data to your own analytics server, and then you can check the data, how your actual user is perceiving your page. So using all this data, we did start performing, we started doing our performance optimizations. We did a lot of performance optimizations. Some of them I will be speaking today, not in any particular order, starting with server-side API cache. So we identified a list of APIs, maybe a config API, data API, data of which don't change much often. Now we implemented a short-term caching for that. So when it comes to caching, you can have either a short-term cache, a medium-term cache, or a long-term cache. Short-term cache is mainly for few minutes, maybe 10 minutes, 20 minutes. Medium-term cache is for few hours. Long-term cache is for few days. We started doing the short-term cache. With this setup, whenever the request comes to the server, it first checks if the data is there in the cache or not. If it's get the data, it return the data, generate the HTML from that cache data, send it back to the client. In absence of cache, request again comes to the server. It will find there is no data. It will go and make an API call. Then it will store that data. It will first process that data. It will store that data in the cache for any subsequent visit. Then it will use that process data, generate the page, send it back to the client. So what was the benefit? What we achieved doing this? The moment we implemented this server-side small short-term cache, the hits on our server got reduced drastically, which means now server has more time to do other critical items. Plus, if there is a less load, that means server would be performing better, the latency would be lower. Then internal API endpoints. So this I discussed during the UI architecture discussion, that our ECS container and our backend is inside the same VPC. We leveraged this setup and started calling our internal APIs endpoint. Benefit was first performance for sure. Internal APIs are much faster when compared to going all over the wire. Then there is a reliability. Internal APIs are less prone to failures than going again all over the wire. Then above the fold content. So what is above the fold content? This is the content which your user will see the moment the page is loaded, and whatever content is below the viewport, those are below the fold content. What we did, we started generating the HTML only for above the fold content, and with that also sending the assets and any of the scripts for above the fold content only. How it helped? It helped in two ways. One is we are shipping now less data over the wire. We are shipping less script over the wire. Then next is, if we are sending less data, less script, that means browser needs to do less work now. If browser is doing less work, that means the rendering would be faster. Then preloading of fonts and critical images, mainly the LCP images. Without preload, the normal flow is browser will download your document. It will see, I need a CSS. It will go and fetch that CSS. Once that CSS is loaded, Then browser will know, okay, I need the fonts. Then it will start initiating the request to get the fonts. Now, depending upon how you are importing the fonts, there are different options. One, by default, fonts are render blocking, but you can make them non-render blocking. So with render blocking, we know you won't be seeing any text. With non-render blocking, the problem would be by the time your CSS or your font is getting loaded, between this two time, browser will fall back to a system default font. And once your font is loaded, then it will apply your font on top of that. In this case, your user will see a flash of uninstalled text, again, which won't be a good user experience. With preload, the moment browser downloads your initial document, we will be sending a hint to fetch certain resource. It can be a font, it can be your LCP images, because we'll tell the browser, hey, you don't know till this point, you will be needing this assets or this resource, but we know. So go and start immediately fetching this. Benefit is, the moment your document is loaded, it will start fetching the font immediately. And by the time your CSS is loaded, font would be already there in the cache. Hence, your user won't feel that flash of uninstalled text issue. Then next is pre-connects. So pre-connects are helpful in a scenario when suppose your above the fold content requires some images from external third party or maybe your CDN networks. In absence of pre-connect, again browser will connect to your origin, download your data. The moment it download your data, it will find I need an image from this other CDN. It will start connecting to that origin first. Once that connection is done, then it will download your image. Again, there would be a lag of connecting. And overall, the user will see the page load as slow. With pre-connect, what's happening? The moment the browser will try to connect to your origin, and somewhere between when it's trying to download your content, we will send that hint to connect to the origin which we required. So that by the time your content is downloaded, browser would be already ready connecting to that other domain, hence speeding up the load. But pre-connect is something which should be used in moderation. Suppose if you have 5-6 pre-connects, it will actually slow down your render because pre-connects are expensive. So in my opinion, you can limit the pre-connects to maybe 1 or 2. Then there is a fonts optimization. So there are two ways mainly through which you can access the font in your page. One is via relying on a third-party services like Google Font or Font Awesomes, or it can be by self-hosting those fonts. Now, only 20% of the pages are currently doing a self-hosting of font. Rest all are either depending upon maybe a combination of self-hosting plus a third party, or they are entirely relying on a third-party services. Previously, there is a benefit of using a third party. Suppose there is a website A and website B. Now, website A is a popular site which user might be already visiting, and if website A and B are depending upon the same font, and the moment the user will open the website B, it will find those font in the cache because of website A. User already visited website A, so those font are there in the cache. But from Chrome version 85, they have implemented a cache partition. So what it means, any resource, cache resource from website A, website B won't be able to access. So in the previous example, even though the font was there in the cache, browser will still go and fetch the same font from the server while the user is opening website B. So that perk benefit is not there anymore. In my opinion, you should always self-host the font. Benefit is, again, in case of using a third party, the pre-connect, what I explained earlier, you need to do that pre-connect, and pre-connect we already know is expensive thing, and there is no cache benefit. So if you're hosting in your own, if you're doing a self-host, it would be much faster to load those fonts. But pre-connect, there is some with self-hosting, there is some overhead. The 75 percentile of the font size is close to 75 KB for a self-hosted font, which is huge. This is due to the fact that if you download a font online, say a Roboto font, now that Roboto font size is close to 60 to 65 KB if you download from online. This is because there are a lot of different characters which is inside the font, which your page might not be using. What we did, we downloaded the Roboto font online. We ran it through tools. One was Zero Lab Tools, which I mentioned earlier, which gives you a good detail of what all characters your page is using. We removed everything extra, whatever is not needed from the page. The result of that was our font size reduced to 7.2 KB. So from 65 KB, the reduction was 7.2 KB. That's a overall reduction of 88%. Now, apart from this, there are other optimizations what we did, like lazy loading of images. So suppose if you are having any image which is not in the current first viewport, you can mark those images as lazy. What browser will do, until and unless your section is not coming in that viewport, it is not going to load that image. Hence, resulting in faster page load in the initial page load, because then the browser don't need to fetch those images and do the extra work. It will only load those images once that section is coming in the viewport. Now there are other options like fetch priority. Fetch priority is mainly helpful in the case if you want to increase the priority of your LCP images, because we want our LCP to be lower. Apart from that, suppose you have a carousel with 5 items, each item having one images. Even though user is just seeing the first item, for a browser it's above the fold content. So it will try to eagerly download all those images. Hence, it might be putting some strain on the browser during initial rendering phase. With fetch priority, you can set the fetch priority high for the very first item, and rest all 4 you can mark those as low. So what browser will do, it will first get for the very first image, it will do all the other work, it will show the content to the user, then after that it will go and fetch the other 4, hence speeding up the initial load again. Apart from that, initially we had lot of inline SVGs. The benefit, inline SVGs to our initial document, the benefit of that was the moment the browser is done rendering the initial document, you will immediately see those images. But there was a problem with that. If you are inlining SVGs in your HTML, initial HTML, first thing is browser needs to do a lot of more work because they need to parse more data. Your initial HTML would be heavy. What we did, we removed those inline SVGs, replaced it with extra outside images, normal images tag. Benefit was two. One was the content, the initial document what we are loading, that got reduced. Then the images, since it's external images, browser is going to cache those images. So the subsequent visit or the load was faster with that. So these are some of the optimization what we did. But now the question is, what was the benefit? Did we achieve anything? So what was the result of that? So the top one is an unoptimized version and the bottom one is an optimized version. I would say not so optimized for the first one, and is the timeline of the page load. If you see, for an optimized version, the content is loaded quite quicker than the unoptimized, and this test was run on a fast 3G connection. So the first content was coming somewhere around 1.5% for an optimized. Going into the detail, the first contentful paint for an unoptimized was around 3.8 seconds. For an optimized, it was around 1.45 seconds. The largest contentful paint again for an unoptimized was close to 3.9 seconds. For an optimized, it was 1.75 seconds. Same thing for time to interactivity. It was also faster after our optimization. Then our initial size of close to 553 KB of data what we are shipping to the browser, that got reduced to 400 KB after doing all this optimizations. JS again, it got reduced by 20 to 30%. That means we are shipping less data and browser would be rendering the content faster. So these are all technical data. Was there any impact on the business after doing all these changes? So we measure our FCP, the first contentful paint, against the conversion for our websites. When our 75 percentile of FCP was 1500, even though it was well within the limit, the moment we move it to 1460, the 75 percentile of FCP, we saw a jump of 12% in the conversion. We optimized it further to 1230. That time we saw a jump of again 17 more percent. So when we went from 1500 to 1230, so that was a change of close to 270 or 280 millisecond. We saw overall jump of close to 30% in our conversion. That's all. Thank you all. Thank you for joining.